Come on in, everyone. Get started up pretty soon. Anybody have any questions while we're waiting? Feel free to ask them. Check something real quick here. Up another person. All right, so it is time to start now. We've got one more person coming in. There's only 6 of you guys, so that's not very good. But I've asked if anybody had any questions. So far, no one said anything. So I asked one more time. Anybody have any questions on outstanding stuff? I will go ahead and point out that I've decided, and I think I might have already done it. If not, I will definitely do it. So don't worry about it. I'm moving the homework that is supposed to be for you guys. It would be due on Monday since you're a Tuesday, Thursday class. I'm going to move it to Wednesday now, just to give you a little bit extra time for this first chapter, this first part of the semester, and that sort of thing. So I'm going to give you a couple extra days for the chapter 17 homework. Uh, the chapter 16 homework, of course, is extra credit. I can't remember what, if any, date is on there. I need to check that though. It's not even, I'm not even sure that I included it in your MATLAB and mastering, so don't fret it if it's not there. But if you really want it, send me a text message and I'll make sure I put it up. Plus, I've already got it made and all that good stuff. So the last time we spoke, I did give you an intro to the atomic theory of matter. I also made a comprehensive argument as to, or hopefully a compelling argument as to why the unified atomic mass unit in grams is 1/Avogadro's number. So hopefully you followed that enough that you can just keep it in your memory so that you don't have to ever memorize 1.6605 times 10 to the negative 27th kilograms. Uh, just because you already know 6.022 times 10 to the 23rd. And I think that's 6.02214 maybe, or might have been 514. I can't remember. But anyways, the more digits you know, the better it is sometimes. But in general, almost all work can be done with 3 sig figs. So you shouldn't really need it more than that. All right, so it looks like no one has, hey Shanda, looks like no one has any questions, so that's good. Let's see, Carly just came in. And we're now all the way up to 10. Hello, 10. We are jamming. All right, so let's go ahead and get started. Again, if you think of a question while I'm talking, specifically, ideally, a question about what I'm talking about, but even if it's not that, it's okay. You can pause me for a little bit. If it's too off the point, off the subject, I might have some issues. Go ahead, Ramsey.
Hi, Professor. I just had a question. I was trying to look at the syllabus, and I couldn't find it on your Canvas, but it's visible for the lab section. Is it the same syllabus for both classes?
Okay, hold on a second. I'm not really sure, but all of a sudden I am hearing sound and it's not coming through my headphones. It's just coming through something I don't know what, and so I can barely hear you. But I heard you say something about the syllabus.
I can repeat if it's fine. Can you hear me clearly now?
Yeah, I hear you a lot better now.
Okay, awesome. Uh, I couldn't find the syllabus on your Canvas page, but it's visible on the labs page. Is it the same syllabus for both classes?
Essentially, but there's a big caveat that you didn't miss, that you might have missed. Your instructor's a loser. so I'm still dealing with some allergies and stuff, so I haven't gotten that done. So what I made available in some of my classes is just the previous semester's syllabus because I really haven't changed it in theory. So you can still look at a previous semester, and other than the due dates not aligning and stuff like that, it's essentially the same. I haven't decided to change anything uh, about it. It's just a matter of I've got to change it and then repost it. It hasn't been posted yet because I just am a loser and haven't gotten it done yet.
No, that's
I was
totally fine.
hoping I would have got it done yesterday. I was hoping I would have got it done Monday. It still just hasn't done. But I do have an all day off tomorrow, quote unquote, all day off tomorrow. So I should be able to knock it out tomorrow. The only thing that stands between me and tomorrow getting it done is two little chihuahuas. So, but they make a very compelling case for me to sit on my butt on the couch and sleep.
That's more than fair. Well, I had one other question.
Yes, sir.
Uh, there's also a passcode on the syllabus quiz that is it the same as the Zoom code's password? What is that?
There's a syllabus quiz. I thought I had removed that. At one time, I did use a syllabus quiz just to make sure everybody knew parts of the syllabus. Since I haven't given you the syllabus, that shouldn't be even available yet. And I hadn't planned on doing the syllabus quiz this semester. That should be moved either way. And yes, if there's a code on it, I have to give it to you guys. So normally when I do something like that, I'll put a code on it specifically so that people will only take it when it's proctored. So normally I put a password on a quiz or test because you're not supposed to have access to it unless you're with a proctor who can give you that password.
Sorry, I have another question. I know it's like three in a row,
Oh no,
but
that's fine. Go ahead.
all types of assessments that we have to do in this course have to be there has to be a proctor, like a physical proctor with us, or can we do them remotely?
So I prefer you to have a physical proctor. So like it definitely one or two of them will be held during your lab meeting. And in that sense, your lab instructor will be a proctor. I usually do them on a computer. So you also have to have lockdown browser, which the computers in the labs already have. So that's the normal plan. But occasionally I will do one that you can actually take at your leisure at home or wherever you want, but the main thing is, in those cases, you would have to have the Respondus monitor and Respondus lockdown browser, which takes the role to some extent of a proctor because it has a camera that's on you. You've got to take the camera, the web camera you're using, and show your workspace. You've got to show me any blank pages you have, that sort of thing. I am putting the actual equation sheet for the tests. I will be putting that in the actual test itself. So I'm not allowing equation sheets anymore. You'll just have a complete equation sheet for your entire semester.
Awesome, thank you so much.
No problem. And if you want any details about how the grading is or anything like that, since I've been so slack on getting syllables, feel free to ask me. You can text me that, and I'll give you all the information. Generally, what I work on is I usually make about 55% of the course grade. Those this semester, it's definitely going to be three separate tests. That allows me two midterms and one final. And what I do is I usually only take the highest of the two midterms, but it gives you three chances to take, basically 55% of your course grade very seriously. What almost always happens is that first face to face test shocks a lot of students because uh, they don't appreciate how much they lean on being able to look at their notes, being able to look up stuff on the internet, being able to use Chegg and that sort of stuff. And then it shows because when you take a face-to-face test where you're not allowed those things, then your grades turn out to be very bad. And that's what we're trying to teach you is obviously how to learn, but also the subject itself, and then how to recognize whether you are learning or not.
Okay. But sorry, I know I'm asking a lot of questions, but I have just one other thing to say. I'm currently doing an internship at the Keurig plant in Windsor, so my
Oh, okay.
hours are pretty long. So that's why I have to drive down all the way to Virginia Beach once a week to do my lab. Will it be possible for me to use my lab window to be doing those exams?
Yeah, that's what we try to do. We try to schedule a couple lab weeks that are quote unquote off. Uh, but they're not really off. They're the time that you come for lab, we're going to administer an exam.
Awesome. Awesome.
Last semester, we were able to do two of them. The chair of the department, I stepped down about a year ago. The chair of the department was shooting for two, but maybe three this semester. So we'll have to see what that turns out to be. Okay. And yeah, I try to watch out for that when people have to travel a long ways, like from Windsor or Eastern Shore or something. I try to accommodate them as much as possible. I feel like I'm driving from North Carolina when I eventually start back driving going to work. So I feel you. Anything else?
All good. Thanks.
You're welcome. All right, so let's
I
get
have one
cracking.
question, but I can get your phone number and text it to you. I had to switch into your lab class during
Okay.
the day, so I actually did swap it, and so but just want to come on Zoom on Tuesday and Thursdays.
Okay.
I'm in everything with your class now. So
Gotcha. Okay, that's cool. No
okay,
problem, Shonda.
gotcha. Okay, yeah, all
If you
right,
have
that's
any
all.
other questions, you can text me.
Yeah, I just got to find where I put your number at. It was on the other Zoom, but
I'll post it here again.
yeah, I had it in my email and I was looking for it so I could just clarify everything with you.
I'm posting it right now uh, in the chat. So there you go. In case anybody else missed it. And in case anybody's missing my email, there that is as well.
Yeah, I
Okay.
have that.
So when we last talked, we had done some calculations. For instance, I did the typical calculation where you determine the distance between adjacent atoms in the lattice of copper at a specific temperature. I think what I used was the density of copper. No, the density of copper. That's a new element I just came up with. It's the mad skills I have. But yeah, it was the density of copper. I think at 20 degrees Celsius, and we were able to figure out. I stand corrected. I'm just looking at my notes now, and no, we never got to that. So let me go on with starting there then. So I could have sworn I'd already looked that up and found I did it, but I must have looked at the other classes. All right. So what we're going to start with is I am.
What?
Yes. Did someone say something? Okay.
Oh, no, sorry. I didn't know I was off.
Oh, gotcha. No problem. So, what we're going to start with is the idea of exactly what the molecular or the weight is on the periodic table. Remember last time, as I expressed, and as you probably learned in a distant chemistry class, hey, little buddy, as you probably learned in a chemistry class, that the mass on the periodic table is sort of read as grams per mole, and that's certainly fine. That's good. But what we also discovered, it's also happens to be unified atomic mass units per atom. So now that we have that, we can actually use unified atomic mass units to do stuff like determine the spacing between adjacent atoms in the copper lattice. So I'm going to do that same thing. I have to share my screen with you, and before I do that, I want to make sure that I remember the density of copper, which is I think 8.3 times 10 to the third kilograms per cubic meter. So let me just double check and make sure that was the right figure. Nope, 8.9. That's what it was. Gotcha. Okay, so now I'm ready to roll because I'm just awesome like that. And oh crap, where's my stuff at? Oh, there I am. Okay. So I'm going to go ahead and click on share screen. And you guys should see my iPad in a moment or two, hopefully. All things going well. And I don't know why I am not hearing him through my system anymore. Maybe I had accidentally hit mute or something on my headphones. But I also discovered my headphones are dry rotted, so I've got little bits of black all over me. My wife asked me if I stuck a chocolate bar in my ear last night. I thought, well, I'm on medication, so who knows? I didn't want to say no because might be a lie. Uh, but it turned out it was just bits of dry rotted fake leather or whatever. All right, so here's the question, and we'll call it an example. And of course, my brother faithfully calls every day during class, and he's done so again today. Don't know why he doesn't learn my schedule. All right. So the example is given that the density of copper. I'm using the periodic table, the symbol, the chemical symbol for the element there. Density of copper is 8.9 times 10 to the third kilograms per cubic meter, and that a copper atom has a mass of 63 unified atomic mass units per atom. Estimate the spacing of adjacent atoms of copper for whatever temp this density corresponds to. So we already figured out that from the atomic theory of matter, that as temperature increases, matter tends to vibrate faster and faster, and that the equilibrium distance between two adjacent atoms or molecules in a solid, for instance, is going to increase as you increase the temperature. So that's what tells us that things expand and contract. So whatever the density is in kilograms per cubic meter, that's obviously going to vary with temperature. It might not vary that much. For instance, you might not get a change in the second decimal place, even for a 10 Celsius degree temperature. But the main thing is that density that I gave you was based on the temperature. I want to say I recall it being 20 degrees Celsius, in which case we're doing this for a 20 degrees Celsius setup, but it's not necessarily the case. So I just left it open like that for whatever temperature the density corresponds. So let me show you how I'd go about working this. What I'm going to do is I'm going to imagine a 8.9 times 10 to the 3 kilogram chunk of copper in a perfect rectangular, or excuse me, a perfectly square solid shape. And because it's 8.9 times 10 to the third kilograms per cubic meter, and I said it's perfectly square, then that means each of the three sides will be the same in length, and that must be in fact a meter by a meter by a meter. So we'll start off with that. So what we have here is a solid that has a width of 1 meter, a height of 1 meter, and a thickness of 1 meter. And in fact, the mass of this is 8.3 times 10 to the third kilograms, specifically because the density is 1 kilogram per cubic meter. That's the Greek letter rho that we use for density. Okay, so what I'm going to imagine with this, and this seems fairly reasonable, copper, being a single atom as opposed to a molecule, should be somewhat spherically symmetric. And of course, depending on what orbital's the outermost, that may or may not be that true, but it's definitely going to be similar from one atom to the next. And the fact that each dimension of this cube is 1 meter, we should expect that you should have basically, let's say, lowercase n atoms in a string 1 meter wide, and then n again atoms long in a vertical 1 meter length, and then n atoms again in a in and out direction.
So what that means is we're going to have, I can draw them like this. We'll say 1, 2, 3. So we're imagining these little atoms are really close like this. And that in fact, they're in atoms there. The same thing here. There are in atoms. And then of course, the same thing here. There are in atoms. So that tells us that n, big N, the total number of atoms, is equal to n cubed, and therefore m, the mass that I just gave you, which equals 8.3 times 10 to the third kilograms, should equal n cubed times 63. Oops. U's per atom. Okay. So n cubed is the number of atoms. If we multiply n cubed by 63 mu lowercase u per atom, then that will actually cancel out the atoms in the n cubed and leave us just a total number of our total mass, if you will. So we have that, and all we really need to do to solve for n is we get n cubed times 63 u per atom is equal to 8.3 times 10 to the third kilograms. And technically, well, I guess it'll be fine this way. But what I'm going to do to solve this is take the cube root of both sides. And what I'll get on this side is n. And to be honest with you, I probably should actually divide this first. Yeah, I mean, mathematically, everything I'm doing is fine, but let me erase this for a second just because it's a little easier to understand if I take this other step first. That's why I was hemming and hawing for a bit there. So what I'm going to do now is take this equation, which was 60. Whoa. I'm going to try writing with the pen as opposed to the eraser. That'll be fancy. 63 U per atom times n cubed is equal to 8.3 times 10 to the third kilograms per cubic meter. And what that tells us is that n cubed is equal to 8.3 times 10 to the third kilograms per cubic meter divided by 63 U per atom. And then I'm going to take that and do one, I'm going to convert the U to kilograms using 1.6605 times 10 to the negative 27th kilograms per U in the denominator. And what we'll get here, of course, is notice the kilograms will cancel out and we'll get atoms per cubic meter. Okay, so I'm going to take the 8.3 e to the third, and I'm going to divide it by, and here I'm going to use parentheses because your calculator knows the proper order of operations. So if you were to type in on your calculator 8.3 times 10 to the third divided by 63 times 1.6605 times 10 to the negative 27th, it's actually going to divide by the 63, but then it's going to multiply by the 1.6605. So you got to use parentheses. Again, I expect all of you, if not at least most of you, know this, but it's just something we got to keep in mind if we're a little rusty on our mathematics. So I'm now putting the parenthesis after the 8.3 times 10 to the third. I'm typing in 63 times 1.6605 e to the negative 27, and that gives me 7.93 times 10 to the 28th. And there it goes erasing again. And notice what happens. This turns out to be the U cancels out with the U. The kilogram cancels out with the kilogram, and you end up dividing 1 over meters cubed by 1 over atoms, so that becomes atoms per cubic meter. That's what the units are. Ooh, that does not look as nice as I would have liked it to, as often happens when I try to fix something. Okay, darn it, another person came in. All right, so now that we're able to do that, what I can do is now I can take the cube root, and that n, which is atoms times atoms times atoms, will ultimately become just atoms. And then on the other side, I'm going to have per meter, atoms per meter, basically. So when you do that, you're actually getting the number of atoms in a given meter. If you flip that over, then you get the number of meters per atom. And that's really what we want. So I'll take the cube root of both sides, and I'll write with an eraser again because that's what the stupid program thinks I want. Is equal to the cube root of 7.93. And by the way, I'm underlining the 3 because I clearly had no more than 2 sig figs. And it's always better to carry at least 1 extra sig fig. So with this in mind, I end up getting n is equal to, now I didn't take the time to go back and type the number in and then put in a cube root. I actually just raised it to the 1/3 power because it's the same thing as a cube root. So hopefully you guys remember that too. So I'm going to say this is 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 4.29. And actually I should probably call that 4.30. Technically when I go to round it properly. So this is 4.3. Dang it. 4.30 times 10 to the 9th. And that is atoms per meter. So 1 over n equals the distance between adjacent atoms. And that is equal to, so now I'm going to take this number and raise it to the -1 power, and that gives me 2.32, carrying 1 extra sig fig again, times 10 to the -10th meters per atom. And that is our answer. Of course, we would report that answer as 2.3, but I have that underlined digit there in case we needed to use that for a subsequent calculation, say in part B or something like that. Again, always carry at least 1 extra sig fig on intermediate calculations. You might also realize that that is comparable, at least on the same order of the size of an atom. For instance, the Bohr radius is 0.529 times 10 to the -10th meters. So the Bohr diameter would be twice that, which is about 1.058 times 10 to the -5th meters. So less than half of that is about the size of a hydrogen atom. And you might not know it, but if you've had enough chemistry or physics, you probably realize that yes, the periodic table increases, has atoms increase in size from left to right and from top to bottom, but the huge increase of the largest atom to the compared to the smallest atom is nothing like huge at all. It's not even, if I remember correctly, it's not even a factor of 10. So to be honest with you, all atoms are on the order of 10 to the -10th meters across, and this is about 2 atoms apart. So a typical scenario for a solid, at least at 20 degrees Celsius, is clearly around each atom being roughly 2 atoms apart. Okay, any questions on that? And I'm saying that just as a record of my experience and calculations. You should, of course, do some of your own, do several elements, and also look up the actual sizes of atoms and check me, because I'm just going on my memory, and I'm 54 years old. I probably has Alzheimer's and can't remember anything. So. So I'm probably just making up stuff at this point. You don't know how much I've been drinking during the day or what. All right. So anybody have any questions on that? I
I have a
apologize
question.
for those people who aren't familiar with my personality. What was that you said, sir?
I had a question. Maybe I missed something. I don't know. How is the mass 8.3 times 10 to the third kilograms when the density is 8.9?
That would be due to magic. In other words, I typed it in wrong, or I wrote it wrong, and now I got to see if my calculator, if I actually put it in right. Nope, I did it wrong completely. That is roughly the figure I got. So yes, you're absolutely right. And I wish you would have caught me on it before, because then I wouldn't have done these boo-boos, but that's still my fault. I'm not saying it's your fault by any stretch of the imagination. So I'm going to put this little guy right here just to remind you. And what I'll do is write the correct answer. I'm just going to put a single slice, swipe through that, just like you do in a lab setting, so that you can still see what the original number is. And now I'm going to correct the number as well. So let's go back to grassroots. I'm going to say 8.9. So yeah, literally, I just copied it wrong. Because remember, I think I told you guys that I was remembering off the top of my head that I thought the density of copper was 8.3. So I looked it up to make sure I didn't make a mistake, and then I promptly forgot it after looking it up and correcting myself. So 8.9 times 10 to the 3 divided by parentheses 63 times 1.6605 e to the negative 27, close parentheses. Okay, this number becomes, in fact, and I'm going to write it in black, it's 8.51 times 10 to the 28th. And then this number, which basically is that number divided by 63. Nope, that number's right. So this number, which is the cube root of that number, is, I'm raising this to the 1/3 power. So this 4.3 times 10 to the 9th becomes, that's why it seemed familiar to me. 4.40. In fact, this one was 4.39. The other one was 4.29. That's why I sort of fell into a lull and didn't think twice about it, I guess. Times 10 to the 9th is that number. And then, of course, you have to flip that over. So I'm going to raise it to the -1 power. And I'm going to put a slash right through here and say this number is 2.27 times 10 to the -10. Okay, so sorry, black results are the correct answers. So the blue was where I used, and thank you, whoever that was, by the way. Who was it that said that? Who told me?
Nathan.
Nathan, thanks, Nathan. That is extremely helpful, no matter what time you do it. So definitely, I appreciate your catching that for me. But yeah, so everything I did was right. The only thing was I blindly took a number 8.9, which I wrote down and ignored it and wrote down 8.3 at least some of the time. You can see up at the top that I did it right next to each other like a dummy. So the true answers are actually the ones in black. But that works out. Anybody have any questions on that? There was no reason for me to do that other than I just wasn't paying attention. All right. So now that we have that, I'll just tell you that opens you up to a lot of different neat little calculations you can do to estimate the size of atoms. I don't know if you know this, but one of the first scientists to ever estimate the size of an atom was Ben Franklin. And the way he did so was basically there was an oil spill and he was at sea and he estimated that the oil was in fact about 1 atom thick. and he knew what the volume of the oil that had spilled was, and he knew what the rough area of the oil spill was. So if you take the oil spill volume and set that equal to the area times one atom's diameter, then you can solve for the atom's diameter, and lo and behold, he got roughly about 10 to the negative 10th meters. So that's a pretty neat little historical fact. But that's kind of the stuff you get to do when you know just a few little things and can use that logic and reason. So I'll go on to the next thing unless anybody else have any questions. All right. This is weird. Okay, there it is. So I was just checking the gas laws and that sort of thing and trying to make sense of where I was in light of me screwing up that. So I've done atomic theory of matter. I will tell you that again, with my atomic theory of matter, we were able to reach the conclusion that, of course, atoms and therefore molecules ultimately, they all vibrate, and that vibration energy, actually, to be honest with you, it's the translational energy, because there's other motion that can happen as well. For instance, the atom, in general, an atom is sort of can be treated like a sphere, and the sphere is such a small radius. It doesn't matter if it rotates about this axis or about this axis or about that axis. That really doesn't matter very much at all. But once you start getting molecules into play, then that's a big deal. So, for instance, you can have a diatomic molecule, or like H2 or O2, or even titanium oxide, and that could rotate about this way. It could also rotate about this way, but rotating about that way doesn't mean anything. So those rotational kinetic energies are completely irrelevant to the temperature. Really, the only thing that matters to the temperature is the translational kinetic energy. So yeah, that is translating when it's vibrating back and forth, but also when it's actually moving more in a linear fashion, for instance, in a gas and stuff like that. So that's something we're going to keep in mind. But with that idea, we know that, yeah, things expand, and therefore we can use the volume of certain things as a variable that correlates with temperature. And any variable that you find consistently correlates with temperature can be used to make a thermometer. The scenario is basically the variable can be used to make a thermoscope, and then once you calibrate it, it becomes a thermometer. So some of the things we've used in the past is the expansion of gases, or the expansion of liquids, or the expansion of solids. I think you all have seen thermoscopes and thermometers that use the expansion of liquids. For instance, a mercury thermometer is basically a glass tube that they've left a narrow, very, very thin cylindrical shape down the middle of. And by making it very thin like that, the volume is allowed to change of the mercury due to, changing temperatures. And since the volume is only allowed to move in the sense that only one dimension can change, the diameter is not going to change in that cylindrical tube, for instance. That makes the change in the actual length quite a bit larger than you'd expect, because it's like you're looking at the change in length, but in reality, you're looking at a change in volume. And you will find out that the change in volume is usually about 3 times as large as the change in length. So that's one of the things you can use. We found that mercury is a little bit, poisonous and causes death, blah, blah, blah. So we stopped using that and we started using toluene. Well, it turns out that's carcinogenic. So we tried not to use that. So now we're using mostly alcohol. Labs still use mercury and toluene and various other things, and sometimes you even have to use other stuff. But the main thing is that's why we don't use those necessarily for human anymore. I will tell you too that they have very limited ranges. For instance, one time I tried to get out of school. I think I was in maybe 5th or 6th grade. I wanted to trick my mom, and she had stepped out of the bathroom for a split second. I ran into the bathroom, grabbed her cigarette lighter, took the thermometer, and held a cigarette lighter under the end, and the thing exploded. I was trying to hold it off, some distance and just let it heat it up for a split second, but I wasn't fast enough and it exploded. So I had to go to school that day. But anyways, that's what happens with them. But luckily, there's other variables as well. For instance, resistance is one, and you can find resistance thermometers in electronic equipment, or for instance, in my dryer, I had sometimes you'll have a dryer start to get so hot that even the paint will start to burn off. And when that happens, it's a very serious fire hazard. Like if you happen to have a basket of clothes or even just straight clothes laying on there, they might ignite quicker than even the paint could start to melt. And if that ignites, then you're going to have a fire in your house. So if you ever see say specifically delicates start to smell funny, like they're burnt or something like that in your dryer, then that's a good time for you to go looking around for the devices in your dryer that act as temperature gauges. And just, they're so cheap, you can just go ahead and replace all of them without even the time to figure out which ones broke. Or if you're really trying to save a penny, there are easy techniques to check for them. So that's some of the stuff you can use in everyday life. Other variables, for instance, if you take a closed container of gas, if you subject it to one temperature, it's going to be one pressure. If you subject it to another temperature, it's going to be another pressure. So you can use a pressure gauge as a thermometer as well. So when we did that, in fact, something very interesting came up. So let me show you what that is. So if you imagine, and just a couple different variables really would work, to be honest with you, but I'm going to do pressure. So let's say this is temperature, and let's say this is pressure, and it turns out something neat happens. So if you were to make a pressure versus temperature graph for, let's say, water vapor, then there eventually, of course, as you get temperature lower and lower and lower, the water vapor becomes a solid. So I have to draw a dotted line for that. It turns out if you also say mercury vapor, well, that makes a line as well. If you use hydrogen, that makes a line. If you use oxygen, that makes a line. And the interesting thing is you can continue doing that over and over and over again for not only elements, but compounds. And they all have their graphs pointing to a very specific point on the temperature axis. And that point specifically is negative 273.15 Celsius, excuse me. Celsius. Okay. Now that means that we have some fundamental idea here. We have a fundamental temperature that's fundamental to everything, because every element we've ever found all of them point back to that same temperature. So that's a non-arbitrary temperature. And unlike the Celsius scale and the Fahrenheit scale, which were based on the freezing and boiling point of water, that's somewhat arbitrary. You might argue, well, we're humans, and it turns out that humans and just about every form of animalia on the surface of the earth depends on water. If you make that argument, then yeah, you could say water's a little special. It's not, quite arbitrary, but there's some probability that we could meet a species, at least around another star, if not centuries from now, around in other galaxies, we might actually find a species for which water's not all that important. They might have found something entirely different. If that's the case, then they would very much see that temperature scale as arbitrary. But that's the nature of the Celsius scale. That's why it has a degree marking. That's why the Fahrenheit scale has a degree marking. And that's also why the actual degrees in geometry have a degree marking, because it was completely arbitrary. The Sumerians, which were using a base 60 system, just said, hey, the number 360 is really convenient to us. A lot of things go into it. A lot of factors go into it evenly. So they used that number, but it was completely arbitrary. They could have used 720. They could have used 1440. All those different numbers are fair game. So that's why we use that. And in fact, this led to the creation of a absolute temperature scale that wasn't arbitrary, and therefore it's not appropriate to use a degree mark for. In fact, it made two of them. One of them is the Kelvin and the other one's the Rankine. So let me give you an idea of how that works. So let's look right here. We'll say this is Celsius. And this is freezing. Of H2O. Oops, I did not mean to put freezing up there. Now I'm going to quickly erase it. That is boiling, of course. And then down here, I'm going to write freezing of H2O. And of course, you all know that under very specific temperature and pressure considerations, the boiling point and freezing point of water are 32 and 212 for Fahrenheit and 0 and 100 for Celsius. So what we're going to do here is just put sort of like a scale, and right here for the Celsius scale, I'm going to write 0 degrees, and this is in degrees Celsius. And right here, I'm going to write 100 degrees. And then I will create another scale. And this scale will be Kelvin. Okay, and that's in Kelvin, not degrees Kelvin. This one right here corresponds to 273.15. And of course, way down here, if I wish to put it, this would be negative 273.15 degrees. And that, of course, corresponds also to 0 Kelvin. And this corresponds up here, the boiling point corresponds to 373.15 Kelvin. And similarly, we've got another scale right here, which is going to be Fahrenheit. And I have no idea if I spelled that correctly. You're just running on a flow here. Okay. Now, this one's a little different, of course, but it still was based on water. So in this case, the freezing point of water was 32 degrees, and the boiling point of water was 212 degrees. And it turns out that absolute 0 corresponds to negative 491.67 degrees Fahrenheit. And then the other scale is Rankine. I think that's spelled properly. Who knows? But anyways, again, we don't use degrees on that guy. But what that means is down here, we have absolute 0. And then up here, we have 491.67. And up here, we have 491.67 plus 212, which is 671.67. I think that's right. Anyways, that should be roughly right. But anyways, that's the way the temperature scales work. What I want to point out to you is that this temperature difference from freezing to boiling is 100. And notice how I write that. I wrote Celsius degrees instead of degrees Celsius. That's a little number keeping trick that I like to use. it helps us, or it helps me keep from making careless mistakes. So I recommend you do it yourself. But technically, I've never seen a textbook actually argue that you should do that. Actually, maybe I did see Giancoli do it, or maybe it was Wilson, Buffa, and Lou. But I do like it. The same thing here. This, however, is just 100 Kelvin difference. Over here, this difference is 180 actually Fahrenheit degrees. And this one too is 180 Rankine. Again, no degree marks on Rankine or Kelvin. Okay. So with that in mind, I'm going to teach you a way, because this is part of what you're supposed to learn in this chapter, teach you a way that we have found from education research to be the most efficient way for you guys to actually learn how to understand the metric system of temperature. In other words, to understand Celsius versus Fahrenheit. Okay. There's actually a nice little poem that works pretty well too. I want to say it's 30 is hot, 20 is nice, 10 is cold, 50 is ice. So that's another thing that's pretty nice. I'll write it here. 30 is hot, 20 is nice, 10 is cold, 0 is ice. So that's a nice little mnemonic that'll help you remember it. But what I want you to see is, from looking at that diagram, we can make some pretty neat conclusions. We can say, for instance, delta T Celsius degrees over delta T Fahrenheit degrees is actually equal to 100 over 180, which you can see is also equal to 10 over 18, which is also equal to 5 over 9. But you could also make it other things. For instance, this would be 0.555, so on and so forth. And also, if you want to go the other way, you can say delta T Fahrenheit degrees over delta T Celsius degrees is exactly the opposite. It'd be 180 over 100. It would be 18 over 10. It would be 9 over 5. It would be 1.8, and so on and so forth. Those are all really helpful. So the way that we recommend, and the way that I'm suggesting you're supposed to do this, even though when you actually take your test, unless I do a face-to-face sort of written test where you have to show me all your work as opposed to a multiple choice, I generally, unless I do that type of test, I'm not going to know really what you're doing. So there is an actual y equals mx plus b type formula you could do. And I was always proud of myself that I had figured out that formula could be easily derived. And I just never committed the formula to memory because it's so easy to derive it. What we're going to show you is a way without doing that. So let me show you an example. Convert 50.0 degrees Celsius to degrees Fahrenheit. Okay, so that's the problem we're going to try to do. And I'm going to walk you through the steps, and hopefully this will help you. So solution 1. How far is the given temp from freezing of water? Now, to be honest with you, you could do that as asking the same question, but saying from the boiling point of water, or any other temperature that you knew was this the number 4 on both the Celsius and Fahrenheit scale. Any of that would work, but this one's this one's dead center between freezing and boiling, so I chose to use freezing. All right. So the answer to this question is, well, the freezing point of water in the Celsius scale is 0 degrees Celsius. So I'm going to do 50.0 degrees Celsius minus 0 degrees Celsius is equal to 50.0 Celsius degrees. Notice how I just put the degree on the opposite side of the symbol there. That way I can remember, oh yeah, that's the number that I've already differentiated from the freezing point. Okay. Now, in the other temperature scale, how, okay, just rewrite it. How far is it from freezing? And again, I mean the freezing point of water. Okay. So this is where I'm going to use my delta T's over delta T's. So I'm going to take 50.0, and of course I wrote it badly again. So I'm going to rewrite it 50.0 Celsius degrees. And I'm going to multiply this by the number that works best for me. Now notice the second row of fractions is the one that has the Celsius degree in the bottom. So that's the most convenient one, or that's the one that I have to use, I should say. And the most convenient one for me would be the 18 over 10. So I'm going to write 10 Celsius degrees under 18 Fahrenheit degrees, because 10 goes so nicely into 50. So when you divide 10 by 50, for starters, the Celsius degree cancels out. Then not only that, this is 5 times 10. So this 10 cancels out with this 10, which is 10 times 1. So that cancels out that way. So all I'm left with is 5 times 18, and 5 times 18 is 50 plus 40, which is 90. Oops. And I had 3 sig figs, and the sig figs used in the fractions are basically to an infinite number, so I can use 3 sig figs here. So this becomes 90 Fahrenheit degrees. Now, step 3 is I want to say what temperature is 90.0 Fahrenheit degrees above freezing. Of course, now I'm talking about in the other scale, which is a Fahrenheit scale. So what I have to do with this is I'm going to take the 90.0 Fahrenheit degrees and add to it the 32 degrees Fahrenheit, which is the freezing point of water. And from that, I'm going to get 90 plus 32 is 122. And that will be called degrees Fahrenheit. So the answer should be 122 degrees Fahrenheit. Okay. Now I'll put a check on there, and here's, I happen to know whether this works or not, but here's how I'm going to show you it. So first off, we know y equals mx plus b is the linear equation, or is the basic linear equation. And if we wish to do a conversion from Celsius to Fahrenheit, we could replace y with F and X with C. And then we just use the fact that F is equal to 32 when C is equal to 0, and F is equal to 212 when C is, or excuse me, yeah, C is equal to 100. So I'm going to do the first one first, and I'm going to say 32 2 is equal to M times 0 plus B, which implies that 32 is equal to B. Now I'm going to use the second one and say 212 is equal to M times, in this case, it is 100 plus 32 because we already just figured out what B was. So this gives us M is actually equal to, notice what we're going to do is we're first going to subtract 32 from 212. That's going to give us 180. And then we're going to divide 180 by 100, and that's going to be 1.8. So now we can say F is equal to 1.8 times, in our case, we were using 50 plus 32. If you multiply 1.8 times 50, then you get 1.8 times 50 is 90. And then you add 32 to that and you get 122. And that's why I was able to confidently put a check mark by it. Okay, so the method that I explained there in blue and red is really what we found pedagogically is most helpful to you guys. I would say that little poem is another thing that actually is pedagogically helpful. So definitely employ both of those, and you'll find that one, it helps your arithmetic skills quite a bit to do this in your head. So you can actually do these kind of conversions in your head on your own and just, use it to practice with your mathematics, to practice your arithmetic and that sort of thing. Anybody have any questions on how I converted 50 degrees Celsius to Fahrenheit? All right, now I got to show you the other way too. So let's do another example. So example. This one will be a little bit more complicated because I'm not going to be able to choose a number that so easily is done without a calculator. Well, that's the number I'm going to choose is going to be that way anyways. So convert, let's say convert, we did do Fahrenheit last time, right? Yeah, we did. No, we did 50 degrees. Okay, good. So let's convert 98.6 degrees Fahrenheit to degrees Celsius. Okay, so that one's a little more complicated. It's even got a decimal place, so the math will be fancy. So let's do it. Number one, how far is this? Now notice in the Fahrenheit scale, 98.6 isn't even halfway between freezing and boiling. It's just a little bit under that. So I could use freezing or boiling, and I think I'm going to do boiling this time. So how far is this from the boiling of H2O? So what I'm going to do is I'm going to say 212 degrees Fahrenheit minus 98.6 degrees Fahrenheit is equal to 212 minus 98.6 gives me 113.4. And this time we write it as Fahrenheit degrees. 2 in the other temp scale, how far is this from boiling? Again, I mean of water. So what we're going to do is we're going to say 113.4 Fahrenheit degrees. Okay. Or actually, yeah. 113.4 Fahrenheit degrees. And now I'm going to choose one of these fractions. In this case, I have to have the Fahrenheit in the bottom. So let's use 10 over 18 because that works pretty nice. So that's 10 Celsius degrees over 18 Fahrenheit degrees. And what I'm going to do is take this 113.4, I'm going to multiply it by 10, and then I'm going to divide that by 18, and that gives me a nice even 63, which we did have 3 sig figs, so I'll carry that digit too. So 63.0. Again, notice that the Fahrenheit canceled out with the Fahrenheit, so I'm left ultimately with Celsius degrees. And then 3, what is a degree Celsius temperature oops. Oh yeah. What is a degree Celsius temperature that far above boiling? Oh, that's not good at all. I think I just screwed up myself. That was weird. Didn't look at that one. Is it back here? Let's see if I did that one. That one. Nope, that wasn't it either. I was just checking to see last time what I did. What is some? So I definitely got that 113.4 is definitely the difference between it and boiling. Then I converted that to a change in temperature, and that change in temperature would be 63.0 change in temperature. And oh, okay. This is okay, that makes me feel better. I was afraid for some reason I was remembering 212 is greater than 986, but I was remembering it backwards. So I was picturing that I was going to be adding 63 to 100. That's not right. Brandon, you have a question, sir?
Yeah, I was wondering, are we allowed to use the equations from the beginning? Like when I see the question convert 98.6 to Celsius, I immediately want to do the
Like the
5
equation I just derived?
5 minus 32.
Yeah,
I
that's
mean,
what I was
we
telling
can
you.
do it both ways.
Unless I happen to give you a test where it's a more traditional test where you're going to write out your work and I grade not only your answer but your work, then I have no way of knowing exactly what you're doing. I'm just telling you that from our research standpoint, we have discovered that it is better for a student in the long run in terms of trying to, they call it metricate, where you switch from the British system to the metric system. It's better to your metrication process if you do it this way. But yeah, I have no way of knowing. So you're certainly fine to do it whichever way you want. Okay. I would say it definitely helps your brain to do it this way as many times as you can, because it's yet another skill set that might come in handy, not necessarily just for converting temperature, but you might find another paradigm where this is useful. But yeah, I'm not going to, unless I do that kind of a test, which I haven't done in years, you should be fine. Anybody else? All right. So what we did find earlier was that 98.6 degrees Fahrenheit was in fact a whole 113 degrees Fahrenheit below boiling. So I should put that here. Just say below boiling. So when I said that far above, that was where the mistake came in. So I will write it back again and say, what is a Celsius temperature that far below boiling? And that fixes everything. Okay. So what we're going to do now is we're going to do 100 degrees Celsius minus 63.0 Celsius degrees is equal to, I think you all can see that would be 38, or excuse me, 37. I don't know why I said 38. And that's going to be 37.0 Celsius degrees. And this becomes degrees Celsius now. So the final temperature for 98.6 is in fact 37.0 degrees Celsius. So let's again check with our little formula that I just derived. I'm going to say this time we want to solve for the actual Celsius. So I'm going to put the actual Fahrenheit in, which was 98.6 is equal to 1.8 times C plus 32. So I subtract 32 from 98.6. And that gives me 66.6 is equal to 1.8 C, and that means C is equal to 66.6 divided by 1.8, and that gives me 37. So we can again say check and check. So those 2 second steps where I'm actually writing in using the formula, that's because you know historically in your life that that formula works. So I'm just trying to give you some confidence that this method does work. Anybody have any questions about that one? Pretty straightforward, right? Not that big of a deal. I will tell you that when I first saw this, I thought it was crap. But I have discovered that one, it's infinitely helpful for my brain just to be able to, I would normally be doing. Okay, I'm not giving you this advice, by the way. Okay, this is very much what I'm doing when I'm driving on long trips. I'm doing calculations like this in my head. I'm a horrible driver and I probably shouldn't be driving, to be honest with you, but that's what I do. And it makes my brain better. Okay. I'm usually pretty proficient at doing pretty big calculations in my head. And that's a good skill. It helps me stave off Alzheimer's and stuff like that. So for that reason alone, I would say definitely worthwhile learning and certainly worthwhile practicing. I do other things as well. Like, for instance, I know that the distance of 1 meter is not exactly 39 inches. And in fact, you can whittle it down and figure out that it's 39 and like 1/8 of an inch and stuff like that. So I actually figure out ways to do conversions from meters to feet that are easy. So for instance, you can always multiply your feet measurement by 3 to get meters, or you can take any meter measurement and divide it by 3 to get feet. But if you want to go to the next level, there's another calculation you can do because it's actually 39 inches, not 36 inches. So basically what I do is every 12 gives you another foot. So I divide the number by 12, and then that tells me how many feet to add to it. And then you can do again for the 1/8 of an inch and so on and so forth. So little things like that, finding neat little ways to work out mathematics are really good for your brain. They're really good for your thinking. They're good for your logic, all that good stuff. All right. So we've now done the temperature system. I've given you some sense of what happens. I'm now going to give you a argument, what I call a heuristic argument for the formula that we use for expansion, linear expansion due to temperature changes. So let me introduce you to that. Okay, I'm actually trying to also move this box that has your faces on it, but I can't for some reason. Oh, okay, I guess I'm just leave it there where I can't see the time or anything. It's just super helpful. Oh, there it is. I got it. There, good. Okay, I moved it. It was covering up my time, so I had no idea what time the class was, what time the class was over or anything. So let me make this argument. What we know from the atomic theory of matter is that matter vibrates, specifically atoms or molecules vibrate, and that average kinetic energy of the translational motion is directly proportional to the temperature. We're going to exploit that later and basically use it to either derive the ideal gas law or use the ideal gas law to derive the formula for the kinetic energy of a molecule for a given temperature. So what I'm going to do now is I'm going to say that the change in length of any particular object is going to be directly proportional. So that little Greek looking alpha thing, it looks like a Greek alpha. It actually, to me, looks more like a ugly fish that we forgot to draw the end of his tail on. But anyways, that's the symbol for proportional. So if you might remember from high school algebra 1 and 2, they'd say X is directly proportional to Y. So you'd write Y is equal to or is proportional to X. And then you'd make that an equation by writing Y equals K times X. Same thing happens here. We're going to have to add some kind of constant to make it equals. But the first thing I'm going to tell you is if I had a 3 centimeter piece of steel and I raise the temperature from 0 degrees Celsius to, let's say, 30 degrees Celsius, I think you all know that it would increase its length, right? Does that make sense? Okay. Now let's do the same thing. Instead of a 3 centimeter piece of iron, let's take a 3 kilometer long piece of iron. Do you think the change in length of the 3 centimeter piece will be longer than the change in length of the 3 kilometer piece, or vice versa?
Isn't it going to be proportional? That's what that means.
Exactly. So I'm going to argue that the change in length is proportional to the original length, which means I'll put L sub 0 there. And I'll also argue that it's proportional to the change in temperature. So for instance, if I change from 0 degrees Celsius to 50 degrees Celsius, maybe I'd expect that to be 5 times bigger change in length than if I change from 0 degrees Celsius to 10 degrees Celsius. Because 0 to 10 is 1/5 of the way from 0 to 50. So I'm also going to put delta T here. And it turns out that there's another parameter. For instance, iron, if I take two 3 kilometer pieces of metal, one is iron and one's aluminum, and I change them both from 0 degrees Celsius to 50 degrees Celsius, I do not expect the new length of the iron and the new length of the aluminum or whatever to be exactly the same. So I suspect it depends on which metal it is. So rather than it just introduce a blatant constant and a number that reflects the idea about the metals and the material you're using being different, I'm going to absorb that extra plain boring constant in the symbol that I'll use for the individual material. So now to make this an equals, I'm going to say delta L is now equal. And here's an unfortunate side effect. The symbol we use is alpha. Okay. So it's going to be alpha L0 delta T. Now, this is the formula that I usually use specifically because I can derive it from heuristic arguments like that, so I don't have to memorize anything. That being said, go ahead, Shannon.
I have a question just to be sure. So that's one is the symbol for proportional relativity, and the other one isn't actually alpha. I was looking at the formula. So that means it's proportional, but then we use the alpha to represent it.
Yeah, it's just unfortunate that the proportionate symbol looks like alpha.
I was trying to look it up because in the book it's a little bit confusing the way it's it goes like that, and I'm like, is it the same or is it a misprint?
Yeah, it's entirely different. The proportional symbol. You can also think of the proportional symbol as like 3/4 of an 8 laying on its side, or 3/4 of an infinity symbol. Okay, and that's called the linear coefficient of expansion. And you can find it in table 17-1. Okay. So now if I remember that delta L is L minus L0, we can get L minus L0 is equal to alpha L0 delta T, which gives me that L is equal to L0 plus alpha L0 delta T, which gives me L is equal to L0 times 1 plus alpha delta T. And that's the formula that most engineering texts have, as well as your book uses, and most people use, to be honest with you. like I said, I don't like that one because it doesn't obviously jump out at me as the physical ramifications, except from years of experience of noticing that if I start off with the first equation, I end up with the second equation. Okay. So you can use either one. They're both the same. It's just a matter of me taking the time to show you that they're both the same. Now, I'll also tell you that the same thing can be done if you want to find the expansion due to or the expansion of a volume as opposed to the expansion of a length. In that case, what you get is delta V is equal to, in this case, they use a different symbol, beta, and it's equal to V0 delta T. And of course, that means V is equal to V0 times 1 plus beta delta T. But here's something really amazing. You know that the length is one-dimensional and the volume is three-dimensional. But check this out. What we have found is that beta is generally about 3 times alpha for a given material. Isn't that cool? All right, so let me stop a second and share a screen differently. I'm going to stop share here. And now I'm going to share the screen quite differently as soon as I get on the right thing, which is not that or not that. Okay. So now let me share screen. Let's do this one. Okay, so there's the formulas I just derived. You can see how they started with the up one up top, and then they got the second one. But this table right here, table 17.1, is really good in that they give you the values that you're going to use. So we do this in physics in case this is your first physics sequence. We ask you questions, and we're going to assume that you have this table at your disposal. In a test, they're usually a little nicer in test banks, and they'll actually give you the values of alpha and beta, but that's not always the case. Okay. So I just want to tell you, when you're doing your homework and when you're doing your practice test, we sort of are expecting you to look these values up. Some of the things I want to point out to you is notice that aluminum has, oh, well, for starters, notice that alpha has to have units of reciprocal Celsius degrees. And notice, yeah, Giancoli did write the degree after the Celsius because it's supposed to be multiplied by a change in temperature, which is the rule that I told you to use, which was Celsius degrees after you subtracted one temperature from another. But that's the unit of it. It's Celsius degrees to the -1 power. But notice aluminum is about 25 times 10 to the -6. The fact that it's 10 to the -6 is the reason that it's so hard to see the small change when you just make a change in temperature of like 10 or 20 degrees Celsius. Okay. So you see aluminum's one that moves quite a bit. Lead's one that moves a whole buttload. Look at that, 29 times 10 to the -6. But another thing that's interesting and important for you to know is look at iron and steel. That's 12 times 10 to the -6. And then look at concrete and brick. That's 12 times 10 to the -6. Does anybody have any idea why I think that's important? If you've not been in the building industry or not thought a whole lot about the building industry, you shouldn't know it all. So this is perfectly fine. There's nothing wrong with you. I would say 99.99% of the population has no idea that that's true or why that's important. So there's a thing called reinforced concrete. And reinforced concrete is concrete that they pour with steel in it. And had steel had a markedly different linear coefficient of expansion than concrete did, then as the temperature rose for a big reinforced concrete thing, the steel would either move faster in expansion than the concrete or vice versa. Either way, the connection between the steel and the concrete would no longer be tensile. It would only be sort of a force that acts laterally. So it turns out that concrete's not that great in tension. Steel's not either, but concrete's not. But when you combine the two with steel and everything, it works out pretty good. And it also works in shear. And of course, it works in bending as well. So all of those things come into play. But that's really wonderful that nature happened to give us this wonderful element steel and this wonderful mixture concrete that actually have about the same coefficient of linear expansion. Brick too, so you can actually, use, for instance, I don't know if you've ever seen it, but when you hang stone on a wall or stuff like that, you normally have to first put down a mesh that looks like screen, and that screen can often be steel. That means it's going to expand and contract about the same rate as the concrete and therefore the mortar and all that stuff. So the concrete and brick is sort of helpful there. You can also see that the alphas do, in fact, look like 1/3 of the betas. So you can see in the second row, that's kind of cool. I'll also tell you that that's also the case about dentists. When dentists try to make a filling for you, it would be really undesirable for them to make a filling out of material that expands at a much different rate than the tooth itself, because if you drink a cup of coffee, there's a chance that your filling would expand quicker than your tooth and make your tooth blow apart. So all right, well, it's 6:40, so technically class is done. I didn't get as far as I would like to, but I consider this chapter extremely, extremely straightforward. I probably, well, for starters, I already have a few videos linked in week 1, so you have enough to work with. You have a ton of examples in your book to work with. So I'm not going to spend more time on this, other than I hope to make some more videos between now and Monday. Which, by the way, Monday we're off. I know you guys meet on Tuesdays and Thursdays, but Monday we're off, so you're not going to have class then anyways. And I did push the homework, instead of it being due on Monday evening at 11:59 for you, I've made it now be due Wednesday evening at 11:59 for you guys. Okay, so you have more time, but I hope before our next meeting, which is Wednesday, I suspect you will have access to even more videos of me solving problems that include, notice I didn't even touch the ideal gas law. I didn't apply this linear coefficient or this linear expansion or the volume expansion and that kind of stuff. So there's more to be done. I am skipping thermal stresses, so I need to write that down. Section 17-5 we're skipping, and I've tried to pull that out of all the practice tests and the homeworks and the tests. Let me know if you find any. I will tell you also that section 17.5 is, in my estimate, one of the most interesting facts. That's the kind of thing that an engineer does. So, for instance, if you have a big body of water that's surrounded by bulkhead or something like that, you might wonder, hey, is that ice when it freezes? Is that going to be strong enough to break my bulkhead? That's what section 17.5 is about. So I do recommend you read it for fun and maybe even take notes, but I'm not going to test you on it. Everybody's free to go. I'm going to wait for the last person to leave before I leave. So thanks for coming, everyone. And you now know that section 17.5, I wrote that in the notes, so you can download the notes from Google Docs. When you get that, you'll see that 17.5 is not done. And conceptual example 17.4 is super helpful. But you can also look at the video that I made for the other class. That's up on YouTube already. So check those out. Have a good weekend, and thanks everyone for coming. And I'm going to stop sharing and do my Forrest Gump. Anybody have any questions? You're free to ask them.
Oh, hey, Professor Younger.
Hey, Micah.
So you sent me that email for that Zoom link the other morning. It didn't show originally, but now it shows. So yeah, I don't know
Okay.
why the attachment wasn't showing, but thanks for that.
No problem. I did discover that evidently when I try to reply to your emails that come from Canvas, I think they just get lost in the ether.
Yeah.
So I don't think you got any of those back, because it kept acting like I'd never sent one. And I sent it 3 times before I realized it.
Yeah, I see the attachment in Gmail now. All right, you have a good weekend. See you, man.
All right, you too. Thanks. How's it going, Nathan? You have any questions?
Yeah, I had a question. So I go on work trips frequently.
Mhm.
So the 19th through the 29th, I'll be on a work trip, which I know is missing some labs.
Okay.
And I was wondering, if in the event that I'm gone on a work trip that isn't planned yet, would I be able to take those tests early, or
I'm going to check out
Anything
what
like
the
that?
19th. You talk about January, right? The 19th through the 29th.
Oh, no. Sorry. February.
Okay, 19th through the 29th. Okay, that looks like. What day does your lab meet? On Thursdays?
They meet on Tuesdays, I believe. Yeah.
On Tuesday. So that means you'll miss 2 labs. If that happens to be one of the test dates, there's ways we can do it. Like if you happen to have access to a computer that has a webcam and you possibly could get a mirror, that's super helpful to us instructors. If you have a mirror behind you, that gives us a slightly better view than just the Respondus lockdown browser and Respondus monitor. But I could set up something like that for you to take it abroad. That's not a problem. And the fact that I post all these online, and the fact that you might actually be able to attend the lecture still, even if you're a distance away, hopefully that all works out. Won't be a problem.
Yeah. The lectures won't be an issue. I already worked it out with my job. The cool thing is my job kind of wants me to get this degree. They kind
Right.
of hired me on that basis. So they're
That's
all about
cool.
school.
Where are you working at? If you don't mind me asking, hold on before you answer that. Let me stop the recording.